table of integrals, and then just doing the integration off of that. There isn't too much that's complicated about that beyond just the initial learning curve of remembering your integrals and using the table to do those. So probably more applicable to you guys. Yeah, you got a question?
Have you finished chapter 9, like in the past few weeks?
Yeah. So we finished chapter 9, went through chapter 10. We're now doing the chapter
Okay.
11 stuff in unit 3-4.
Okay, cool.
You're talking about unit 3-4, yeah?
Yeah.
Yeah, sweet. And all those recordings there if you wanted to catch up on those. But yeah, based on where you guys are currently at, I don't think you probably don't need too much on these fundamental ones, more so probably on the application side of things. So let's see if we can start with some of these external responses. We'll take it nice and easy to start with. We've got a big piecewise going on, and we're just going to be doing some, I don't think, too complex analysis of these functions. So let's have a look. After taking medication, the concentration of the drug is increasing and then gradually decreases over time. A second medication is taken, concentration will therefore rise again, and we got this function that is essentially modeling the concentration of the drug over the 12-hour period of time. So you could imagine some peaks and some troughs as it rises and falls. Probably has to do with the breakpoints of these functions in the piecewise, right, as they sort of taper off into each other. If we do a quick analysis of all of those functions, they are all quadratics, right? They are negative quadratics, actually. So they're all going to have different maximas. We can see vertical translations are changing. We can see horizontal translations somewhat change. And so this being an external response, one of the first things we can do is just graph this if we wanted to get an idea of what the full thing looked like. Part A is just asking us to figure out the concentration 2 hours after the first medication was taken. We don't necessarily need to graph for that though. So what I'll do is I'll start getting the graph going. In the meantime, have a think about how we're going to answer 1A. Feel free to jump out as soon as you have an idea, by the way. I'll just do this in the background while you guys have a think. Be all the functions. Now just to set proper window. So we get that sort of shape going on, where the y-axis is going to be the concentration of the drug, and the x-axis is going to be the time in hours, 12-hour period, all the way up to x equals 12. Cool. Okay, so we can see it's created in 3 separate parts. Got this first part here, second part where it tapers off, and then the third part where you get the next rise. Question 1. Find the concentration of the drug 2 hours after the first medication was taken. Yep, you got a question?
Yep, so I think I had an idea for that one. So I guess you'd assume that T is the time. So that's kind of the variable. So you'd assume that if it's after 12 hours would be like t equals 12 or something like that, and then you kind of substitute depending on which rule it fits into.
Yeah, correct. So we got a full 12-hour period from 0 all the way to 12 for the t value. So yeah, we can definitely imply or infer that t is going to be in terms of hours. So if we're going to have to do the drug after, well, 2 hours after the first medication was taken, which function is that going to be relevant to?
First,
First
first
one.
one.
Absolutely. First one is defined from 0 to 3. So 2 hours after first medication means we're going
Yeah.
to be using F1 of 2.
And then do we just substitute it into that first one as well, right?
Yeah, exactly right.
Okay.
So if we have a look at what it was defined as in the CAS, that was F1. And so all I've done is I grab a copy of that. Whoops, not like that. Grab a copy of that in the variable section here. Or you could just literally type out F1. Either way, gets you there. Yeah, as far as how you give your answer, just be sure to put the unit in there. In this case, it's going to be milligrams per litre as per the description in the question itself. So this one you would say concentration equals 40 milligrams per litre. That'd be about it. Any questions about that? If not, let's have a think about part B, finding the maximum concentration during the first 3 hours.
Would it be 45 milligrams per litre?
Yeah, I have a sneaking suspicion it certainly will be. What gives you the idea that it might be 45?
I looked at the graph and went to the x value of 3,
Mhm.
and it's labelled as the maximum, and the y value is 45.
Yeah, that's right. So, and even looking at the function itself, it's a quadratic. It's got a turning point at 3, 45. So the peak of that's going to be 45. Absolutely.
Would this like definitely be a tech active question?
Yeah, as an extended response, it's default assumed that it's going to be tech active. If not, you can clearly see that most of this is doable without, in fact, probably all of this is doable without needing a CAS.
Yeah, that's what I was wondering. Like,
Yeah, like sketching these quadratics yourself would take no effort, really. You don't even really need to, you know where the turning points of each of them are, you know that they're negative quadratics. It'll take maybe a bit to figure out where they join up. You just be sort of solving each of those little breakpoints of what's f of 3, what's f of 9. But yeah, by default, you assume extended response to be tech active. But yeah, 45 milligrams should be it during the first 3 hours. Yes. Find the concentration of the drug 6 hours after the first medication was taken. What are we going to do there? Let's see. This one may or may not be tricky.
Because it has a t value of 6, you would substitute it into the second equation if you weren't going to do this on your calculator.
Mhm.
So then you would have 6 minus 3, which is 3 squared. So you would have negative 9 plus 45, which would give you a y value of 36, meaning that it would be 36 milligrams per litre.
Yeah, 36 milligrams per litre. Perfect. Yeah, nice. Yeah, so 6 hours after the first medication was taken, even though the thing that I thought might be a bit of a gotcha could be, yes, it's defined from 3 to 9. I think I've seen the error before where some students will basically, seeing that it's 6 hours, but this one's like shifted 3 to 9, they might, I've seen it before where they'll cut down the 3 hours into like subbing in t equals something different to get there, which may be relevant for some wordings of the question, but by and large, you're pretty much doing exactly what you did there, which is perfectly fine. Part D might do a similar thing. You know, when did the patient take the second medication, and what is the concentration of the drug at that time? We have to start thinking about things in terms of the shape of the overall graph that we have. So when did the patient take the second medication? something told to us in the question, more so told to us through the shape of the graph. And you have to make a few minor assumptions about when the drug would be exactly taken. You got to forego a few real-world limitations of it.
You'd assume that because the second equation is showing like a decreasing gradient, that wouldn't be where the second dose is taken.
Mhm.
So then I would say that the second medication's taken at T=9.
Yeah.
And then the concentration of the drug at that time would be 9 milligrams per liter.
Yeah, so choosing T=9 because it is the boundary right before the concentration shoots back up. Now let me just quickly validate. I think, this should be, oh, that's right, it's undefined for that. Let me try that again. T=9 for 9. Yeah, 9 milligrams per liter on that one. So yeah, what I was kind of pointing at with the real world limitations is technically, when you administer medication, you're not necessarily immediately injecting it directly into the bloodstream. But we got to forego a few of those real world complications and just say, yep, concentration's increasing immediately, or about to immediately increase at that spot. So we can assume that's our best guess for when the next dose was taken. Perfect. Cool, we did answer both parts of that, the time and... Actually, that's a good point. Do we have like a reference for when the time actually is? It just says a 12-hour period. So I guess when you're giving your answer for when did the patient take the second medication, T=9 is perfectly fine as an answer, but a more complete answer would be something to the effect of 9 hours after the first medication was taken, because that'll use the same terminology that has been persistent in all the questions so far. It's a slightly more refined answer, but both will get you the mark either way. Cool. And then finally, what is the maximum concentration of the drug during the full 12-hour period? Very similar question to, what was it, part B. Let's see how they get this one sorted.
You could just look at it kind of from the graph, highest y value.
That's it. Highest y is going to be right at the very tip top of that. You can be doubly sure of that because the function itself is got a turning point at 12,54, just based off of well, it's kind of hidden on this, but it's definitely in the textbook. Shifted right by 12, up by 54, so without even really doing any math, we can see that it's just going to have a maximum concentration of 54 milligrams per liter. Nice. And this one didn't suggest anything about giving the time, so you would just need the concentration as your final answer there. So that's a fairly basic version of your extended response. Pretty much all you're doing is looking at a graph and then using a bit of reasoning to figure out what the graph actually means. Concentration being your y-axis, time being your x-axis, and then all the numbers given to you have to state with reference to in this case, the 12-hour period, right? If it gave you like literal times, like 1 o'clock, 2 o'clock, you would have to eventually then convert that back into your 24-hour time or your AM, PM time. So little things like that is where those might get more complicated. But yeah. Question 2 looks quite similar. We've got the height of a ride at a park, given by another piecewise. Finding height at the start of the ride would be the same thing as what's the concentration in the bloodstream at the start of taking the medication. Basically the exact same question. Height of the ride at each of these horizontal distances. Again, you're just subbing those values in. finding horizontal distance when height is 6 meters. If it's a height graph, you're just subbing height equals 6, although that one is a bit more interesting because we have limitations based on the fact that this is a piecewise. So maybe rather than doing all of these, let's have a think about the complications of this. So before that, let's get super clear. This is a height graph with respect to the x, where x is the horizontal distance from the start of the ride. So basically, I'm assuming you have some sort of loop-de-loop thing going on. You have a start point that's immediately all the way left. You have an end point that's all the way to the right. X is measuring from left to right. So when it says finding horizontal distances, it's referring to finding x, horizontal distance of x. I'll start defining these in the CAS while you guys have a think about how we might address part C.
Well, if the height's 6, then you have to figure out which equation it will fit into, kind of the restrictions they're given. So you'd use the first one, because the height is 6, and then you'd just kind of, I think you just kind of define it as 6 equals negative 0.02, and then just solve for x.
Yeah, that's right. So you've identified the challenge, which is you can't really just do. Maybe you can actually. Maybe you can define this thing as a full piecewise and just do h equals 6, solve for x. But defining piecewise in the CAS can be a bit like, all at once is kind of a bit whatever. So doing it in parts like that seems fair enough to me. That's how I would do it. I'll just finish defining this linear and then we'll do what you suggested there. So basically solving first function equals, it was 6, wasn't it? Yes, 6 meters for height, comma x, and then trying to identify, okay, do any of these solutions fit in the domain we were given? Yes, one of them certainly does. Doing the same thing for b of x. Do any of those fit? X equals 8.5. Yep, one of those certainly fits as well. And then lastly, the c of x final function. 0.2 bracket x take 13 all squared plus 3.2. b of x equals 6. Any of those fit? 11 to 16, yeah, so then 9 is going to fit on that one. You can avoid having duplicate solutions if you just put domains on each of these solves. Furthermore, I do suspect you could just create a piecewise and do it all in one solve. Let's just quickly see if that's doable. So for piecewises, first things first, get the define up. Then the thing next to the book here, it's almost got like the same sort of structure as the piecewise. I use this one specifically. So, 1, 2, and 3 look kind of similar, even 4 maybe. This one I've typically used for the piecewise. This might work. I've just defaulted to using this one because you can set the number that of entries that you need. Whereas I think from memory, yeah, you don't get a choice at that one. So let's go do that. We want 3. I've already defined each of these, so we can just sheet that out real quick. All that's left would be to give these domains proper. So 0 to 7 should be inclusive. 7 inclusive, and 11 exclusive, 11 inclusive, and 16 inclusive. Let's find out. Does this just do it? Yeah, that's pretty cool. Was there only 2 solutions there? 1.83, 8.5. Oh, this one wasn't sorry, it's supposed to be from 11 to 16. I said that this was going to be in there when there, when that definitely is less than 11. Yeah, so only 2 solutions made sense for that. Cool. So yeah, you absolutely can create a piecewise for that if you prefer, which honestly sounds like it's a better idea because as we can see here, I made a mistake when I assumed that 1 was inclusive when it was not.
Yeah, I feel like for this question it's not super necessary with like the things that they ask, but I feel like it depends on the question. Like you can just kind of look at what they're asking you and then see if you'll use it or not.
Yeah, correct. Like this one in this case, everything. Well, the last function didn't actually end up needing it, but it's kind of hard to see if it's going to need it or not. Well, maybe it's got a vertical translation of 3.2, but it's a positive quadratic is the thing. That last one, so it's hard to say. Like, yes, it should hit 6 for sure because its turning point is below 6, but it's pointing upwards. So it's hard to say whether that last one is going to have 1 inclusive or not. So in this particular case, yeah, you probably needed all 3 to really figure it out, and putting it a piecewise is probably just the safest bet. But as you're right, yeah, sometimes you just flat out don't need it, right? Like part A, height of start of the ride, you don't need all of it. You just need to define the first part. Sweet. Okay. I know question 3 tends to get people sometimes, working the speed, distance, time. Those formulas tend to be a bit confusing when applied in these like application questions. So maybe we'll have a look at one of these. Okay, a coach leaves town X, maintains a constant speed for 4 hours, stops at town Y, and the next trip is town Z. Okay. So with these ones, by far the best idea is going to be to get a picture going of what's actually happening. Trying to get some diagram. So far, I'm aware we have 3 towns. We've got town X, town Y, town Z. For the first duration, it is 80 kilometers an hour for 4 hours. So let's do that. 80 km per hour, 4 hours. Stops at town Y for 3/4 of an hour. So 3/4 of an hour is there. 2.5 hours at 80 kilometers to Z. Once again, 80 kilometers per hour, and that one was 2.5 hours. 2.5 each. Then, a second coach leaves town Z at the same time. So I'm assuming the same time as the other one left town X. Yeah, I'd even. Yeah, I'm going to assume it meant the same time the town X one left. And that goes straight to town X. We're not told anything about speed, but we are told the duration. So that one goes straight from Z to X, and it's 5.5 hours, 5.5 hours. Cool. Construct functions that describe the distance from X of each coach at time t, domain, range, and rule. Cool. Okay, so we want a function describing journey 1, which can be like the red, and journey 2, which can be the green there. And it's going to be purely in terms of the distance from X. So in other words, for journey 1, at time 0, the distance should be 0. At journey Z, the journey Z train at time 0 should be whatever the distance is from X to Z. So we have 2 functions. D1 of, I'll just make it in, actually, it's D at T, so D of T. D1 of T and D2 of T. Those are the 2 things we want to have here. that's where we're at currently. I won't say much more. Let's have a think for now and see if we can come up with any ideas. Even if it's one of the things that can be good is to sort of take a step back from the question entirely and just be like, okay, what do I know about distances? What do I know about speeds? What do I know about times? How are they related to each other? Maybe another thing to highlight is our distances are, what unit do we have? D in kilometers. So we're creating these in terms of the kilometers. Another hint for mapping the journey could be to think about what chapter this was in. So this chapter was about functions and relations fundamentals. It introduced ideas of domain range. It introduced ideas of inverse functions. It did piecewises. It did, what else was it? Yeah, maximal domains, but that's kind of the same as domain range. What else did it introduce? Let me quickly just take a step back. Yeah, difference between one-to-one. So really the only new idea here is going to be this piecewise idea, which is a big hint on how you might model these functions.
Well, I think would this be a piecewise because there's two, I don't know what they are, like two trains, I don't know, coaches, like which are traveling at the same time, but then one's going away from X, one's coming towards X.
Yeah, so it's not a piecewise because there's two coaches involved. It's a piecewise because there are stages to the journey that are happening. All right, so if you were to think about how you would describe this journey in words, you would say the train started, like let's say we're doing the left-hand side one. The train started at X, it traveled at 80 kilometers per hour for a total of 4 hours before it stopped at Y. It stopped at Y for 3/4 of an hour before then moving on.
Okay.
And so each of those stages can be modeled as separate equations. So it's kind of misleading how I've done these. We're not going to do these in one line, but in fact in several stages, or maybe just D1 because D2 was kind of just direct.
Yep. It was kind of like how the questions we did before, how they went from, they kind of had the restrictions from like 0 to 3, 3 to 9, but, and it's kind of had the T in the middle, but instead say how for the second one, it's like as if we would kind of skip the second one because the times elapse in the middle, but there's no actual movement because we're taking a break.
There's no movement, correct, but we're not actually tracking movement. We're tracking distance from X.
Yeah.
So it's not that there's a 0 there, but there is whatever we left off at there.
Okay. Yeah.
That's a good little distinction to make. But yeah, so now we know the idea that we're going to break down into 3 separate journeys, at least for the first coach. The question now becomes, how do we actually create the rules that model each of these? So let's think about that first journey, right? Just this first little bit here. We're traveling 80 kilometers an hour for 4 hours. I mean, that's pretty much it. We're going to assume it instantaneously gets there. It doesn't have to accelerate up or accelerate down because it doesn't tell us any information about that. So if we were to create a model of how far away we're getting from X relative to time, how might we do that? You can even do some little mental math in your head, right? Like if we're traveling at 80 kilometers per hour, how far should it be at 1 hour? How far should it be at 2 hours? And then you can start thinking, okay, I've got these dotted out points. Oh, that's the relationship. That's the rule that it's going to be. And if dotting them out doesn't help too much, you can also think of what is the relationship between speed, distance, and time. Well, speed is distance over time. So if you want a distance equation, you rearrange for d, giving you speed times time. So as long as you know the speed that you're traveling and the time duration, you can create your distance equation. If speed is the variable, it stays as s, and time is the constant. If time is the variable, then s is going to be the constant. Okay, let's think out loud for a sec. So back to the idea of just sort of doing some mental math. If I'm traveling 80 kilometers an hour for 1 hour, how far have I made it from where I started? That'll be 80 kilometers, right? 80 kilometers per hour. 1 hour is just 1 hour has elapsed. I've made it 80 kilometers from where I left the last time. Over 2 hours, it'll be double that. 80 times 2. 3 hours, triple. So on and so forth. It is linear, directly related to the speed that I'm traveling. So it's a constant speed the whole way. The only thing that's changing is how much time has elapsed. So in other words, 80t. T is the variable. We're doing distance in terms of time. If I have t equals 1, that would be 1 hour. 80 times 1, 80. 80 times 2, 80 times 3, 80 times 4. So that gets us our rule. Is it fair enough on that? These are, you get in your head about these sometimes when in reality they tend to be a little bit easier than we're expecting. Is it fair enough how we got there? Surprisingly complicated to arrange it in seemingly easy answer. All good? Cool.
Yep.
Okay, well that's the rule now. We just need to give a domain. Hopefully this will be a little bit easier to spot. So domain is x, or in this case t. What's a relevant or appropriate domain for this?
Would it be like the maximum distance that it would travel away from x?
So if we look at our function d of t, distance would be y-axis stuff. Time is our x-axis stuff here.
Okay, then it would just be the maximum time, no? Because the most it'll travel in terms of like when it's moving, the most it'll travel will be 6.5 hours. Because I assume we wouldn't include the break time, or we would.
So for just this part of the journey, I get that you're adding it all up, which is fine. You can do that as like as a quick check that you've made it for the full, you made the full piecewise correctly. But with the piecewise, you tend to want to focus on little sections at a time.
Yeah, so it'd be 4.
Yeah. So we're going to do something like 0 to 4 for that one there. You can make it inclusive or exclusive. It's, just make sure that if you make one inclusive, make the other one exclusive. By convention, they'll typically leave it off that way, but both are technically the same. To answer your other question about whether we leave this bit off, well, if we did leave it off, we're not including this part in our model of the journey. So we do need to have it in there. What we do need to have is a way to express that. The easiest thing to really think about would be time duration that we're there for. So it started at t equals 4 for sure, because we got there at t equals 4. And then 3/4 of an hour later, we're now at 4.75, basically. So that tells us the duration for which we are at this stage. The next question is therefore going to be, okay, well, how do we actually define this rule that describes this stage? It's not a 0. Think about, remember, our y-axis is what's being described by this rule, and our y-axis is distance from x. So in other words, we need to figure out what is the distance from x at this point y.
Would it be 320
320.
kilometers?
Yeah, exactly right. 320 because you did 80 by 4, 80 kilometers per hour for a total of 4 hours. 320, and it's a constant 320 because there's no motion happening there. We were told that it's perfectly stationary, so we have 320 without any variable associated with it. Nice, well done. And then the last leg of the journey, very similar to part 1, so I'll let you guys take a stab at that one. Very similar. This last leg of the journey, we're still traveling 80 kilometers per hour. We're doing it for a duration of 2.5 hours this time. So exact same, more or less, information as we had from the first rule, from x to y. How are we going to implement that for our last and final rule?
It'll be kind of the same, so it'll be 80t and
Yep.
then just the adjusted domain. So for 4.75, then inclusive t, another inclusive, up to, I don't know why I cannot add this in my head.
That's all right. It's the live pressure, mental math when you're on the spot.
7.25.
7.25. There we go. Sweet. Cool. Okay. That looks like it's it. Yeah, 80t, because again, it's 80 kilometers per hour when t is hours, so that makes sense. 2.5, and leading off from where we left off. Cool. That gets us the full first duration, the first thing. We do technically have to give the range of it as well, but since we're already in the same headspace of getting our distance equations, maybe we'll just pause that for now and do the second journey this time. So the second journey was express. Now, this one's a bit... Actually, maybe we do need to think about the range of the first one first, because if we think about that second journey, we don't actually have any speed information. We just have the total time it took to go from there to there. So maybe we should think about range of this just so we get a better idea and understanding. So range of this function, range being all the possible y values that fit into it. The lower bound should be quite clear. It'll be the upper bound that might need a bit of thinking. Oh, actually, I've just spotted a quick issue with this, and it took me a moment. It'll make sense if I actually sketch this. So this is what I mentioned before with the whole, when I was talking about like the C of T, the first one we had a look at with the different horizontal translations across the different domains. We'll see at least a little bit of what I was discussing there. So if we have 80 from 0 to 4, we're quite happy. If we have 320 from 4 to 4.75, whoops, didn't put the X in there. you should also be quite happy. This one is going to be a bit strange now, I think. Oops. Why can't I type things anymore? Have 4.75 non-inclusive to 7.25. And I didn't even put the X in there. Jesus. How many errors do you want to make? Okay. Now we had a duration from 0 to 7.25. And we had some pretty big Y values. So let's just like, I don't know, 800. Now, having sketched what we've discussed so far, we can see a clear issue. There's a break in our function. The first and the second, pretty nice. Does anyone know, and this is a tough thing to spot without, yeah, I mean, it took me a moment to remember it. Does anyone know why there's a break in that? Or at least any ideas why there might be?
So what was the question again?
So if we look at what we've just sketched, this is the rule that we created for our piecewise, and it looks all right up until this point here, where there's a break in it. Clearly, we shouldn't, in the real world, just have instantaneously changing distances without no time duration. Do we know why there's a break here, and maybe how we can potentially fix it?
Wait, is that kind of where? Wait, is that where you graphed the break, like where the code just took a break?
Yeah, so the coach took a break
okay,
at this
yeah.
horizontal bit, but then we tried to make the remainder of the duration of the journey, when we plotted our ADT, it ended up over here rather than joining neatly here. Any ideas why?
I'm not sure quite how to word it, but would it be because when the time is, what time is it that it changes? Like
4.75
was it? Or 4.75?
Yeah.
Yeah. Is it because then if you're assuming that you start driving at that time, your distance will immediately increase rather than gradually?
So no, this is an error. We shouldn't have this. We should have it such that it connects here. The issue we're trying to point out is why do we have this, and how can we potentially fix that? It's got to do with the fact that these rules are identical, but described over different domains. Or in other words, if you don't change anything about the rule, what you've basically done is take this horizontal line and just sort of rub out the middle, because we haven't graphed that part. So in order to have this connect here properly, we have to fiddle with the y-intercept portion of it, shifting it down a certain amount so that it does actually connect here. That's the main thing I was trying to sort of get to with the original function that we started the question 1 with. Because if we, actually, do we still have that graphed? I do, yeah. If we look at these functions, right, like these both have horizontal shifts of 3. In order to get this one to marry up properly, we had to shift it over a certain amount to make that work. What we haven't thought about here is how we shift this to marry this one up. So in other words, it's still going to be ADT because the gradient of it is the speed. We need to make sure the speed is still maintained, but we essentially need to find a way to drop it ever so slightly so that it does match back up with 320. So finally, we have ADT plus or minus some offset such that it equals 320. We want to figure out what offset gets us to reach there at a specific time, that time being 4.75. So at 4.75 for time, we want to introduce some offset, some vertical translation, such that we start where we left off. Now that's going to get into some weird decimal stuff, so I'm just going to quickly cas that one out. So we have 80 times t, which is 4.75, plus our vertical translation equals 320, comma, x. That's going to give us negative 60. So if we then adjust that, unless I've made a mistake, this should now marry up properly, which it does. So this is the common pitfall that everyone, including myself, will fall for, which is, oh, yep, it's the same rule, just over a different domain. Not quite. It's mostly the same rule. It's just got to be shifted over ever so slightly to make sure that we do marry it up with the rest of where we left off. So that's explained the issue. I'll just take a quick pause to make sure that the way we've solved the issue makes sense. Is there anything in there that needs further clarification? Perhaps another way to think about it would be when you're solving your polynomials that have like a bunch of unknowns, but they have points in them. You're trying to find the intersection point between two incomplete rules. So we're just subbing in a known point, that being 4.75, 320. We want to make sure that this rule also has that exact same common point. Okay, cool. That should be good for that then. So that should now complete the full function of the first one. Yes. We do need to give range now. So now that we have the full thing sketched, range should be fairly trivial to think about. We have a very clear lower bound. The only thing we'd have to think about how to do would be the upper bound, which shouldn't be too much to think about. How might we get that upper bound? We want to range all the y values in there. Clear lower bound of 0, it's all the way down here. And because it keeps increasing, the tallest possible y value is up here. So we're going to get that nice and easy by just shoving in the 7.25 into that last function. So f6, 7.25, going to get us a final value of 520. That's important to know. So we have our range, 0 to 520. What does that actually mean in terms of the scenario? Like, we got 0 to 520, but like, what are the units involved? Think about our function d of t. What are the units involved in that range value?
Kilometers?
Yeah, kilometers, absolutely. So 0 to 520 kilometers is the full range of the journey. What does that mean we can now think about as our what do we now have the information of about our scenario? Like, we had some distance, we had some time information, we had some speed information, and that was pretty much it for both of the durations of the journeys. This now gives us distance information. So the range of 0 to 520 implies what about this scenario? With a reminder that this rule was depicting the duration from x to y and then finally to z. This rule depicts that entire distance map. 0 to 520 implies what about our journey? Okay, that's okay. I'll phrase it in a different way. If I wanted to know the distance from x to y, or y to z, or x to z, what would I do? That's okay. So what I'm trying to get at here is the range values are our distance values, right? This is in terms of kilometers. So a range of 0 to 520, because we were mapping the journey from x to z and all the stops included, that simply means that the distance from x to z is 520 kilometers. So furthermore, we could even split that up. From x to y, for instance, that's just going to be the connecting point from this part. So sub in t equals 4, we can say that 320 would be from x to y. From y to z, you got to do a little bit different. You would either subtract the 320 from the 520, or you would find the distance between subbing in t equals 7.25 into this, and then subtracting 320, which, I mean, we kind of already know this gets you to 520 anyway, so it's kind of the same thing. But yeah, so if this is 520, then that means this would be 200 here. So the reason why that's going to matter is because with that second journey, we only had time information. There was no speed associated with it. So we need to try and figure out some other way to get some more information. Because we have our speed equals distance over time equation. So as long as we have any two of those, we can get the third and have a full complete journey. We had our time information, 5.5 hours from Z to X. We didn't have any of these until now. We do know the full distance. It said it ran express at a constant speed. Well, technically it didn't say it ran at a constant speed. We've got to kind of assume. Assuming a constant speed, so solving for speed, we have our distance total of 520 over a total time duration of 5.5. We can now get the speed coefficient for our linear. So the speed is equal to the distance of 520. That was covered over a duration of 5.5 hours, which I will quickly cas out. 520 divided by 5.5. So somewhat nasty fraction. It's going to be 1040 over 11. Just a bit of an interesting one. In kilometers per hour. The only reason that matters is because if we think about the pattern that we had before, it was pretty much just speed coefficient times time. So this is now our speed coefficient. So all we would do for the rule is just slap a t on that and then put our domain, which in this case, if it's 5.5 hours, it'd be from 0 to 5.5. So to conclude, d2 of t, 1040 over 11 t, and it was from 0 less than equal to t less than equal to 5.5. Any questions about any of that so far? These do get a bit weird.
I was wondering, like, in general with these types of questions, are there any like good like CAS tricks or anything that we should know?
Good CAS trick specifically. So good CAS trick, graph, that'll quickly spot any errors in the rules that you're creating, which, yeah, by far graphing it's going to be a really good idea whenever you have these sorts of things. And this isn't really a CAS thing, but getting a diagram is really good. CAS tricks for this one in particular, can't really say too much beyond that. You kind of really just use it for your own sort of error checking and making sure that things make sense. Doing some CAS solves to make sure that the functions all line up as you expect them to. Graphing it to make sure, again, it lines up as you expect it to. If we think about the other ones, that's pretty much all we did for all these other questions. We graphed it, and then we used the graph to infer some information. What else? Some of these, you start getting into like maximums and minimums of distances. You can start using your Fmax and Fmin equations, or calculus. You can do your derivatives. It's mainly there. I'd say the most applicable use of the CAS for these kind of things is going to be to get an idea of what you're looking at, a good picture, which can be supported by your own picture of the scenario as well. Okay. Cool. We do need a range for the second one, but it is just a linear at the end of the day. You're just going to sub in t equals 0, t equals 5.5, and in fact, there's no real math to be done here. You could sub in 5.5 just to validate it, but we should know that it's going to come out to be 520 anyway. Range is our distance values, so if they are going from the exact same spot from x to z, then if it doesn't come out to be 520, we've made a mistake. So maybe I should just double check that. So 1040 over 11 times 5.5, yeah. That's going to once again get us the 520. So 0 to 520 as a range for both of those. We're about to hit time. Let me know if there's anything I should clarify further. Because this part B, we're not going to have too much time to think about, unless you want me to sort of talk out loud, and I could screen share the answer and we can kind of just talk about it at a higher level if you like. But before that, if there's anything I should clarify, let me know.
Yeah, that makes sense.
Sweet. Okay. If anyone wants to stick around for some bonus learning for the rest of the whatever couple of minutes, what they wanted us to do was to figure out when do these coaches intersect each other. Now, not literally intersect, otherwise that would be catastrophic. And when do they first meet each other on those separate tracks? It's not as complicated as it might seem because we do have the CAS. We can just sketch these out. So we can see we got a copy. I am definitely screen sharing this properly. We can see we have a copy of the function that we created with all the relevant times and distances. We would just be plotting the second one. And it is a negative linear because we're basically going in the opposite direction. We're starting at the maximum possible distance away from x, and we're going to our smallest possible distance away from x. So when they meet each other, it's just going to be that crossover point. So in other words, you would do d1 of t equals d2 of t and solve for t in a CAS solve. Alternatively, if you didn't create a piecewise for it, you would just use the first section of that piecewise and equate that, because we have the luxury of knowing what that graph looks like, which is, again, one of the bigger benefits of using a CAS for this sort of thing. Cool. If there's anything to clarify about that one, let me know. Otherwise, yeah, that'll be about it. Thanks, guys.
Thanks, Chris.
No worries.
Thank you.
No worries.